What we have here is a UV visible spectrometer, and within that spectrometer there's a location where you place your quartz cuvette, or sometimes a plastic cuvette, and that has to be placed in a very specific way so that the beam of light that passes through it actually goes through the transparent parts of the cuvette and not the opaque parts. So that's very important when you actually place your cuvette in the spectrometer. Now, what we've got here is paracetamol, and this is what you'll have done your work on. And what we see is an absorbance maxima at 243 nanometers, and it has an absorbance of 0.67 absorbance units at that point. Now, this is very ordinary for a drug or for any organic molecule that in particular has these double bonds in it. And these are very useful in identifying the particular molecule, but they also allow us to quantify the amount of that molecule present. Now, this is the spectrum of lycopene, which was extracted from tomato puree. And what we can see is that this is red in colour because it's absorbing very much in the red end of the spectrum. This end is very much the blue end of the spectrum. And the reason that we've got that going on is because the blue light and the green light is actually passing through the sample, and only the red light is being absorbed. And that's because we've got these conjugated double bonds that increase the wavelength at which absorption occurs from what you get for a single double bond, which is 165 nanometers. So when you get two double bonds together, that absorption can be increased to 217 nanometers, and of course that increases as you stack up the conjugations. And in this case we've got a lot of conjugations going on. It's a good idea to explain how the UV-Vis spectrometer works. And what we have on this particular instrument, if we go into the laser pen, you have a light source, and that produces white light, which can be split up into its constituent components of light, and they are sequentially passed through a cuvette containing our sample, or in this case it's a blank, which in this particular case is ethanol. Most normally that's water. Now what we do then is the light is then passes on to a detector, and what we're recording here is an idea of the intensity of that light that has passed through to the detector. It's not a measure of flux of photons that have gone through. That's really quite important to remember. Now, the reason we do that is because it's actually, you have to buy a very, very expensive piece of instrumentation to detect single photons and count single photons and get a light flux like that. Now, what you can do is compare things very, very cheaply with electronics. And so what we do in this particular case is we compare ethanol versus our solution of lycopene in ethanol, and so we get the spectrum ultimately of lycopene out of that, because what we're using is a system of subtraction. So this background recording will be subtracted from the sample recording to produce a spectrum. Now in this case it goes through exactly the same procedure. The white light split into the components, systematically pushed onto the sample. The sample will absorb certain wavelengths. It'll be very different to the background sample, and the transmitted light is detected. And this time we have that subtraction that goes on, and of course we are able to get to a spectrum from that. The useful aspect of a UV-Vis spectrometer is the ability to measure concentration in a solution. Now, how that's done is through the Beer-Lambert law, And we discussed on the previous page this value of I0, which was the intensity of light that the detector received at a particular wavelength passing through our zero concentration sample or background sample, and the I value here, which is the intensity of light that passes through the actual sample at a particular wavelength. Now those wavelengths are going to be the same, and what we have here is then a logarithmic relationship between the two. And what we can say is we call that relationship produces a value of absorbance A, and that's the direct reading you'll get from the instrument. Now the interesting part of this is that we can relate that to concentration through this little bit of the equation here, where we have our Greek letter epsilon, our path length, so that's literally the distance that the light is passing through the actual sample in the background, and then our concentration. So we have two prefactors there to concentration, and it forms a straight line, and in this particular case there is no constant that's added to this. You only have the epsilon and the path length of the cell. Now, because the path length is 1 centimetre, we don't need to worry about that in terms of the maths. All we need to know is about the epsilon value. So if you were to plot a concentration against absorbance for a particular molecule, what you'll get out is the slope having the value of epsilon, and that's characteristic of an individual molecule at a particular wavelength. And that's a very good way of characterizing a particular substance and saying we believe this is this particular molecule because it absorbs at this wavelength with this particular value, and so we believe that this is an identifying feature. You normally need to do other means of identification as well. One method of identification usually isn't enough. UV-vis spectrometers are typically used in a pharmaceutical environment to identify the concentrations of unknowns. Now, when I say unknowns, we know what the substance is, we just don't know how much is there in a particular volume. And how we can do that is by construction of a calibration graph. And to do that, we need to use known values of concentration. So in this case, we're using sodium salicylate, and what we've done is created concentrations of known values. We've put those into the instrument, measured them against a blank, and these are the absorbance values that we've actually got out from the instrument. And what we've done here is plotted those values. So we've got concentration along the x-axis, and then absorbance along the y values, and so we actually construct a calibration graph, and each of those values corresponds to a point here. Now, in the BP, you normally have to use at least 5 points to produce a calibration graph, and this proves that you've got a straight line, and when you actually do interpret an unknown, it's important that you don't try and extrapolate that line into this region or above this region. You can only carry out your measurements within this particular region of that calibration line. Now, having plotted our calibration line for known values, we can use Excel to produce a trend line, and that trend line will have a linear characteristic. So we've got our y, which is absorbance, and our value of x, well, we've got 68.31x minus 0.0006, which is our intercept value. And as we said previously, the slope is our epsilon value, and our intercept is pretty much 0 here. So that matches up to what we saw in the previous slide very, very nicely. Now, if we have an unknown concentration, but it has an absorbance of 0.2 when we put that into the instruments, what we can do is use that to estimate the concentration of that particular solution. And we do that by simply substituting in the values to our trend line. Now, if we go to here, we can actually say, well, y is going to be equal to the 0.2, which is the absorbance value, because we've plotted absorbance value against concentration. And we can say our 0.2 is equal to our 68.31x minus 0.0006. And we can rearrange that to give out the value of x, which just happens to be underneath where I'm talking to you from. And so we can actually solve this little equation and give ourselves our concentration from that.